He's the director of the North Carolina State Quantum Initiative. Please welcome Greg Byrd.
Hello, everybody. I'm leading off. I'm going to go to the next slide and say, this is what you should know about quantum computers. Now, I only have a few minutes, so I only can tell you some of what you should know about quantum computers, but let's get into it. Well, if you watch movies or TV, or you look on stock figures and you see, you ask, what does a quantum computer look like? This is what you kind of see. You see this big, scary looking thing that's always, well lit in some spooky background, and it's always some powerful AI, all-powerful thing, right? Well, that's not quite what they are, at least not yet. But I do want you to know that a quantum computer is not a bigger, faster computer, right? It's not the same as the computers we have now. And the reason we're talking about them is because they're different and they can do different things. So the basic idea of how they're different comes to this basic unit of information. So in our computers, we have a bit. A bit is either, as you probably know, 0 or 1. And that's how we represent information in our, what we now call, classical computers. A quantum bit, called a qubit, also has the 0 and 1 states, but the quantum state is a combination of 0 and 1. It's called a superposition of 0 and 1. So there's two different outcomes, 0 and 1, and it's got these numbers associated with each outcome that are related to the probability of observing that outcome. And so one qubit encapsulates two numbers, okay? Where a bit is 1 bit, a qubit is 2 numbers. And things get really interesting if we have 2 qubits, 4 different outcomes. Each one has this number associated, which again is related to the probability of seeing that outcome. And so we have 4. 2 qubits gives us 4 numbers. If I were to write down the state of this, I would have to write down at least 4 numbers. 3 qubits gives us 8 numbers. You probably know where this is going. 4 qubits, 16 numbers. 5 qubits, 32 numbers. It grows exponentially. So the amount of information we can encode in qubits doubles every time we add a new qubit. And so if we have this ability to create, manipulate, and observe qubits, we have this very large space of numbers that we can play with and search for solutions. Okay, so that's what really makes it quite different than classical computers. There is a catch, though. Remember, with my 5 qubits, I have 32 numbers, but I can't look at all of those 32 numbers in a quantum computer. If I ask the quantum computer, what is your state, one of those numbers comes out. Not one of those numbers, one of those outcomes comes out. And it's generally the most likely one, the one with the biggest number associated with it. But we get a classical piece of information out. So I've got these 32 floating point complex numbers, and I get a 5-bit number out, okay? And not only that, is when I do this act of asking it, what's your state, all the other numbers go away. It becomes that state and that state alone. So this is different behavior than what we have with classical computers. So the best things we can do with quantum computers, the best algorithms that we develop, are ones where we work alongside a classical computer. Quantum computers are not going to replace classical computers. They're going to work alongside them and do the things that quantum computers do best. And so we need to send in some information. All the information we have is classical, right? We send in bits to initialize this state. We send in bits that represent the evolution that we want these numbers to take, And all that happens, very efficiently and very fast in a quantum computer. And then we do this measurement and we get a moderate amount of classical data out. So those are the kind of algorithms that we look at to exploit this power of quantum computing. Now, the other thing I want you to know about quantum computers is that there are several different technologies that people have developed and are developing that can implement this idea of a qubit. The one at the top, that's an IBM System 2. They use superconducting circuits to create this two-state system. It might be neutral atoms that we're going to hear about in the next talk. It might be ions. It might be photons. So all these different physical representations of the qubit, you'll hear about different kinds of quantum computers, and they have their pros and cons, and nobody really knows ultimately what the winner is going to be, right? What the most prevalent quantum computer is going to be, but everybody is making progress along these lines, and we will be using quantum computers in the near future. But we're still in early days, right? Some people say it's sort of like where we were with computers in the 60s, perhaps. This picture's from the 40s, so maybe not that far back. But what I'm going to leave you with is these takeaway points. Number one, what I've talked about, quantum computers allow us to have this large solution space, but we only get a single answer, so we have to carefully craft our computation to take advantage of that. What I didn't talk about is that this quantum state that we create is very fragile, and over time it decoheres, it goes away. And so we can't do a lot just yet to manipulate our qubits, but something called quantum error correction is going to be the one that corrects this, allows us to run long things. As I've said, we're not going to replace classical computers. We're going to augment them. Progress is really happening fast. You'll see a lot in the press about things. And you don't need a PhD in quantum physics to use or program a quantum computer. And that's what I want you to know about quantum computers. Thank you very much.
Awesome. Good stuff. I remember playing Qubit in the arcades in the 80s. It was super fun. Orange guy, he jumped around. It was a delight. All right, excellent. Q&A time. So I've got my assistant Alicia back there. We'll start right here, and then Alicia, we can get that one over there. We'll start over here with you, sir. What is your question for Greg Byrd about quantum computers?
Yeah, I'm wondering how well Bayesian neural networks could approximate the quantum superposition. So you essentially have a distribution of probabilities and kind of what the trade-offs are there.
Yeah, it's a little more nuanced than what you could do in a neural network. It's not just probabilities. We have this correlation between these states called entanglement. So there are aspects of this quantum state that aren't represented strictly by probabilistic computing. So it's more capable than probabilistic computing. So I know that people are trying to use AI to model some things that quantum computers can do, but I don't think it's something that they could actually mimic in a very substantial way.
Awesome. Thank you for the question. Alicia, who do we have over there?
Hey, Greg. Thanks for putting this together and sharing. Part of me wants to look at this as an evolution from 8-bit to 16-bit to 32-bit to 64-bit, but I don't really feel like that applies. What type of problems are quantum computers really good at solving?
I think that some of the later speakers are going to address this directly, but the ones that are most mentioned are simulating other quantum systems. So there's a quantum system that we want to understand. We model it using a quantum computer, and we learn things about it that way. Optimization is one, lots of possibilities in finding a solution quickly. There is a large activity in quantum machine learning. And then the one everybody's heard about is Shor's algorithm for factoring integers, which will change the way we do cryptography. So those are the ones that people sort of talk about as the closest. So chemistry, physics, problems like that are probably the most near-term applications.
It'll still never replace Excel. All right, other questions. We got one back here, sir. I will come back to you. What is your question on quantum computers?
Yes. For some years, I have wanted to see some quantum computer code, you know, line by line, operation by operation. Where is a good place to get an introduction at that level?
IBM Quantum Learning.
Well, short and to the point.
It's all
All
written,
right.
It's all written in Python.
Ma'am, we will get you right here.
Just a quick question for you that work for IBM Quantum Innovation Center. What happened to the 7-qubit processor that was developed back in 2000? Do you know anything about it? You know, because there was an initiative from IBM back in 2000 where they used the 7-qubit processing computer, and I was just curious if you knew anything about that.
Well, back in that time, you know, 5 or 7 qubit machines were all that we could really build and control and be very precise with. Now, IBM has 150 qubits on a chip. They've built a chip that has 1,000 qubits, but their main thing is 150. So the state of the art now in terms of number of qubits, 100 to 150 is, and maybe 200, you know, are kind of where things are in terms of what people are building and able to reliably use these days.
All right, Alicia, I think we've got one over there.
Hi.
Hi.
First exposure to quantum computing, and the mind boggles from, and I'm not sure. But the question is, we are already facing challenges with like these huge data centers to process LLM and machine learning, but it sounds like these things can do a lot more processing with a lot less. So I'm curious to understand how that would have an impact on the power, the environmental, this land usage, et cetera, for data centers.
That's a really good question. First of all, these computers currently are very expensive, right? So that's one thing that I'm concerned about. They do require significant power. There's a lot of cooling. Some of these have to work at very low temperatures, and so you have to put a lot of power into the cooling. But I have seen some people believe that one of the early advantages of quantum computing would be to do something at a lower energy level than like a very large supercomputer or not. I'm not an expert in that, but that is one of the areas that that I've heard people say as a potential advantage.
All right, folks, give it up one more time for Greg Byrd.